Mr. Carlson here. Let's talk about reaction mechanisms. So, a reaction mechanism is essentially just a series of steps which will lead to an overall reaction. So, if I look at this chemical reaction that we've got right here, we have NO2 gas combining with carbon monoxide gas to make NO and CO2. Now, if we think about this reaction right here, what we have and what we would assume we have happening is that we've got this NO2 molecule here, and it's going to basically collide with this CO molecule. And when that happens, they're going to react, and this is going to lose an oxygen to CO to make CO2 and give me NO. And like we would be safe in assuming that, right? Because that's what our balanced equation is showing us, that these two are reacting to give us these two things. But as it turns out, the reaction is actually probably a little more complicated than this. There's probably more going on than just this colliding with this to make these products. And one of the reasons why it probably is a little more complicated than just that one-step process is that if you were to actually do this reaction, one thing that you would notice is that you would detect the presence of NO3. NO3 would be what is called an intermediate in this reaction. So if you were to actually run this reaction, you would notice that NO3 would kind of pop up in the middle of this, but then it would kind of go away. So basically, somewhere between these things reacting and these things being produced, you make this NO3 somewhere in the middle of that reaction, but then it kind of gets used up and it's not part of the products in the end. So that means there must be something more going on between these things reacting to produce this in order that NO3 kind of shows up in the middle of the reaction and then kind of goes away. And so instead of it just being one step of this colliding with this to make these, we have what is called a mechanism. So we break it up into two different steps here, which are called elementary steps. These are elementary steps. So if I look, this is a proposed mechanism. So this is like what we think could be happening in this reaction, is that instead of NO2 colliding with a CO, instead what I have in the first step is two NO2 molecules actually are going to combine to make NO3 and NO. And then in a second step, that NO3 is what actually combines with the CO to make NO2 again and CO2. So instead of just these two things combining in one step to make these, I break it up into two steps where the NO2s combine first to make NO3 and NO, and then the NO3 is what actually combines with the CO to make NO2 and CO2. And if I were to add these two together, now whenever we add reactions, what we're going to do is we're going to cancel out anything that is the same on the left-hand side as it is on the right-hand side when I add these reactions together. So for example, I see that I have NO3. It's on the left-hand side of this reaction, and it's on the right-hand side of the top reaction here. That means when I add these two reactions together, they are going to cancel out. They're going to go away. And I see that I also have an NO2 on the left-hand side of this reaction and an NO2 on the right-hand side of this reaction. So again, those are going to cancel out. And now if I add these together, for the total on the left-hand side of these reactions, I have NO2 and CO. So NO2 and CO. And then on the right-hand side, I have NO and CO2. So if I look, when I add these two elementary reactions together, these individual steps, I end up with the overall balanced equation, right? So the overall reaction is these two things are reacting to make these two things. But in that process, though, we actually made some other things, right? We made NO3 first, and it was the NO3 that reacted with the CO to make that CO2 and NO, okay? So these two elementary steps are what are actually happening in this overall balanced equation, okay? Now, a couple things about elementary reactions that we're going to need to understand. So this is a key thing right here that we need to know and remember. And it is that the rate law for an individual elementary step, you can actually write the rate law for that step based on what is called the molecularity, or in other words, what molecules are combining in the reaction. So we have been talking about rate laws, and one of the things that we learned is that, and I've got it right here, for an overall equation, we've learned that you have to look at like the experimental data, and you have to see like how is concentration affecting the rate, and then based on that we write these rate laws where we figure out the orders of each reactant, right? So for this overall one, this is the experimentally determined rate law. But for an elementary step, so just for a single elementary step, if you know that this reaction right here is an elementary step, you actually don't have to experimentally determine the rate law of an elementary step. For an elementary step, you can just look at what do I have reacting, and I can write the rate law for that. So the rate law for step 1, I can just look and say, well, I've got 2 NO2 molecules combining, and that's it. And so I can write my rate law based on that. I would go rate is equal to our rate constant K times the concentration of NO2, and then I would raise it to the second power because I have 2 of them. So basically I'm just using the stoichiometry of the balanced equation for that elementary step to write the rate law, which we could not do for the overall balanced equation. I could do it for then step 2. So step 2, if I wanted to write the rate law for that elementary step, I would do the same thing. So rate is equal to our rate constant K for that reaction, and I've got NO3, which I just have 1 of them, so it would be raised to the first power, which we just leave blank, and then times the concentration of CO. And again, there's only 1 of those, so that would be raised to the first power. And so there'd be my rate law for the second step there. So if you know that a reaction is an elementary step within a mechanism, you can write the rate law for the individual step. But you cannot write the rate law for the overall reaction unless you have like the experimental data for the overall reaction, okay? And the last thing is this, then, for a mechanism, so if we propose a list of steps for an overall reaction, there's 2 things that it needs to satisfy in order for that mechanism to be possible. So the first thing is the sum of the elementary steps need to add together to give the overall balanced equation. So we saw that up here, and that makes sense, right? So if your steps don't add together to give you the overall balanced equation, well then obviously your mechanism's not going to work because it's not going to give you the overall balanced equation. So if the proposed mechanism, the steps that there are, they need to add together to give you what the overall equation is. That's the first thing. And the second thing is that the rate law for the slow elementary step, that one needs to match the experimental rate law for the overall reaction. So in most proposed mechanisms, what you'll see in a problem is that one of the steps, and there could be like 3, 4, 5 steps, this one just happens to have 2, but one of the steps is going to be listed as, it'll say to the right of it like this, it'll say slow, and the other ones will say fast. They might be in parentheses, kind of like this. And so what needs to happen is that the slowest step, and it's not always necessarily the first step, It could be the second one, could be the third one. But that slow step, that's the one that's going to determine how fast the reaction goes. So basically, the overall reaction can't go any faster than what your slowest step is. So the rate law for the slow elementary step, that one needs to be the same rate law basically as the one that was experimentally determined for the overall reaction. So let me say that one more time. The rate law that you write for the slow elementary step, okay, needs to match the experimentally determined rate law that you have for the overall equation. And so if we look at this one, we actually already wrote the rate laws for each elementary step. Here was the rate law that we wrote for the slow step here. It was rate is equal to K times the concentration of NO2 squared. And that does match my experimentally determined rate law because this is the one for the overall equation that was determined by experiment, and it matches my slow step. So therefore, this mechanism that we propose, these two steps, that's a plausible mechanism. This overall equation could happen in these two steps because these two steps add together to give me the overall equation, and the slow step, the rate law for the slow step, matches my experimentally determined rate law.